So thank you very much for coming, to you and to the people that is online. So for this unusual time for a seminar today, but that was the only way in which we could fit Pablo's talk this week. So Pablo Docampo, so he's a physicist. He made his PhD in Oxford, right? And then after Oxford, he went for a postdoc in Munich in the LMU, as far as I remember. Then he moved to Newcastle. That was the first time that he got already the leadership, I would say, of his research. And now he's in Glasgow, where he's also leading a group on perovskite, solar cells, and all the things that Pablo will tell us this afternoon. So thank you very much for being here, Pablo, for the first time in San Sebastian. And
thank you very much. Don't worry, I won't keep you here for too long. I know it's 3 p.m. and it's end of the day, so I'll keep that in mind. So what I wanted to talk about today is some of the research we do on heavy halide perovskites. If you're not familiar with this, they're just a hot new thing in photovoltaics, and there's two key things that have been kind of cropped up as a technology. And that's the ion migration and stability. These have been the things that have not worked quite so well for it, and it's very important to address ways of so we can get the technology actually up and running. Okay, so I like to start my talks with an acknowledgement because sometimes you forget to do the acknowledgements at the end. So I want to acknowledge all the people that worked on all of this stuff. So the stuff I'm showing you it spans from Munich to Glasgow. So these are all the groups that I've had throughout the time, and just you'll see bits and pieces from all of these people. Okay, so what do we do? Most of the work we do is understanding how these materials crystallize. And we use this information, the physics of the materials, to understand the device physics. So this is kind of what we do. Then we try to apply it into new applications. So we've done LEDs, transistors, waveguides. We've put in fibers. We've done a little bit on some additional different concepts, and we've looked at a lot about how to stabilize the structure. I'm going to focus on this bit today. So. Okay. It doesn't like the pointer anymore. Hold on. I'll just go with that. Okay. So, perovskites. Why are we so interested in them? So, you might be familiar with the structure. So, it's got a spacer. You've got a lead center and some halide ions on the corners. And the interesting thing to me, and this is why I still show the slide after all this time, is that these are semiconductors you can print. So, they're solution processable. And if you look at this plot over here, so this is looking at the absorption as you get close to the band edge. So the sharper this slope is, it means the fewer defects it has, or at least those defects do not absorb light. It's a measure for material quality. So normally, if something is full of defects and it's not great, you'll see a very broad curve. What you see here is that the perovskite absorption is not that different from gallium arsenide, which tells you that these materials crystallize in very high quality from these inks. So it's very interesting from that point of view. It's a very defect tolerant system. And currently we're at 25, almost, I think it's 26% now efficiencies, which competes quite well with silicon. I should say in a small area. We're not competing in the big area. I think I have to go manually. So the reason they work so well is because the conduction band and the valence band arise from the lead halide bond. So you have a third element, which is the spacer cation, that doesn't actually play into the electronics. So it's just from the hybridization of the lead and halide orbitals. What that means is that if you exchange the halide, or you tweak the bond angles, or you twist, whatever material property you want to tweak, that will affect your electronics. So that's the main way we have of tweaking the system. So this comes out as you can basically tune it. So this is some work we did on nanoparticles. You can see that basically you can tweak the lattice, you can exchange the halide, you can exchange the cation, and it just works. This is very unusual. This is very, very unusual. If you work in CdTe, you can change selenium for sulfur, but there's a limit to how much you can incorporate. With perovskites, we seem to be able to cover pretty much the whole spectrum, and it usually works quite well. So the other thing is that if you wanted to use perovskites in any kind of, you want to do research on perovskites, you end up, you just need something like a spin coater. This in contrast, if you want to do classic inorganic semiconductors where you need, you know, a big investment. Or if your spin coater is under repair in America and you need something in a fix, you can make your own spin coater with an old computer and a fan, and just a power supply. This is, of course, a hypothetical scenario that never happens. The neat thing is that you can really process them easily. You can actually make paintings with them. They're just, it's an ink. You can do things you can do inks with, and that's kind of the interesting part. Of course, you can do more interesting that like for high throughput, and you can print them and so on and so forth. So it's an interesting space. A solution processable has really good optoelectronic properties that you'd see in gallium arsenide, and you know that makes them interesting. Now let's get into the meat of the talk. So they're semiconductors, but they're also ionic conductors. What that means is that we've got lots of vacancies. When we crystallize, this is a solution process, it crystallizes very quickly, and there's always defects when it crystallizes. The defects don't play a role electronically, but there's still atoms missing in the lattice. Okay, so those are the ionic defects that we're going to be talking about for the next 20 or so minutes. Now, there's three possible defects. You can have the lead moving, you can have the halide moving, or you can have the organic cation moving. This one, the lead moving is very unlikely. It's got an activation energy of 2 eV. That's very unlikely to happen. So the lead atoms are pretty much static. This one, the organic cation can move, but very slowly, in the range of hours to weeks. Whereas the one that is quite mobile is the halide vacancy, right? So this is what we normally talk about when we talk about ion migration in perovskites. We're talking about a missing iodide atom or a missing bromide atom. And the thing here is that the population of these vacancies is actually bigger than the electronic charge when we illuminate it with light. So the ionic population dominates the device of physics, okay? This is why you can't just take a classic semiconductor physics model like COMSOL or whatever and plug it with a device like it doesn't work. You need to use drift fusion, anything that takes into account the movement of these ions. In terms of the physics of the material, when we apply an electric bias, those ions will move to the grain bond, to the device interfaces, to screen off this external bias, and that will shift your bands. Now, the obvious outcome of this is that if you're not familiar with J curves for solar cells, for a solar cell to be good, you need to have a square-looking thing. The less of a square it looks like, the worse it is. Now, this is the same cell, just coming one way and coming back. It's just a hysteresis loop. You can see that one of them is a lot worse than the other one. And that's because you've moved the ions to a position where they're now hindering charge extraction. Okay, so the ions sloshed around, are accumulating in one of the interfaces, and they catalyze the combination, so you lose charge. This is why you observe that loss. Okay, so you would be, you know, we think of them as they're not great. We don't want to have them. And this is a bit of explanation of what happened here. Basically, when we first applied the field, we moved the ions to the interfaces, which bends the bands. When we turn the field off, the ions remain in place. So now they bend, you get some a dip in the conduction by the Bell's band, which accumulates charge carriers, which increases the combination. Okay, don't worry, we'll come back to this in a second. So as a field, we thought, okay, ions are bad. Let's get rid of them. How do you get rid of the ions? Well, the easiest particularly for chemists is to just make bigger crystals. Normally, slow down the crystallization, and then you end up with your defects. If you end up with a single crystal, ideally, you end up with a fewer number of defects with ions, so on and so forth. So basically, we like big crystals and we cannot lie. So we're always trying to minimize the ions. So I'm not going to bore you with the exact details here. There's many ways of targeting, ways of crystallizing the materials. I'm breezing through this quite quickly, but the important message here is not the specific route. It's that we can make very large crystals that are all oriented in the same direction. We target an intermediate phase, which then that crystallizes out, and then we convert that to the perovskite phase. And it works really nicely. We basically use these solvent additives to achieve that, and it basically gets incorporated into the structure. It directs the growth, and then we convert that to the perovskite structure. Now, what I'm going to show you here is a GWAX measurement. Is this something that you're familiar with? Not really? Okay, so GWAX is created in the incidence wide-angle X-ray scattering. Okay, so what you do is you shoot a beam into your sample, and then you've got a 2D detector. That way you can collect. So normally on a Gaussian scale, you only collect data from whatever is in that perpendicular path. With a 2D array, you collect from all the crystals in the sample. What this is good for is it gives you all the possible orientations. Okay, so if you were to put a polycrystalline film, you would see a ring. Okay, you would normally see a ring because you collect from all orientations equally. Now, using this approach where we go to this intermediate phase with direct growth and then crystallize it out, we end up with spots. Okay, that is more or less what you'd get with the silicon wafer if you did that, right? So our materials are very ordered. They're not single crystal, but they're very large, and we show that we can tweak the orientation from something that is lying like flat to something that is vertical. So we can tweak the orientation of the crystals. The crystals are very large. You can get up to 30 microns, and it is a single crystal all the way through. So we did some TL measurements. You can see the diffraction pattern is the same throughout this whole bit, which shows that it is a single crystal. Again, that's not the important bit. The important bit is coming now. So when you do this, when you minimize disorder, when you make these crystals big, or oriented in the same direction, you minimize the grain boundary defects, okay? And that actually leads to an increase in the mobility of the material, okay? So we did some time of flight measurements. We simply excite near one of the contacts, apply an electric field, and measure how long it takes the charges to get to the other side of the film, and you get a better result for these nice big crystals. Looks like everything is working as expected, and then we made a device. And the one you would expect to be the best, the one with the biggest crystal, the less amount of disorder, is the worst material. Well, what have we done wrong? We've minimized the ion defects. We've done everything right, and yet our device is not right. It's actually the worst one of the lot. When you start looking into this a little bit, when you get this kind of S shape, that normally indicates you've got some kind of energy barrier at one of your collection interfaces. So one of your contacts not working great. Okay, so we looked into that. It wasn't that. What we did is that by minimizing the number of defects, picking out the grain boundaries, what we've done is we slowed down ion migration. We just made it really, really, really slow. And so we actually caught it in a configuration that led to a worse charge extraction. So the message here is it doesn't matter if you clean up your crystals to the infinite degree. You can do single crystal solar cells. You still have ions. You can never get rid of them. So you're going to have to work with them. So we started looking into this and thought, okay, great. So we have to work with the ions. What can we do with them? Well, the first step is what can it tell us about the physics of the system? We've already seen that depending on the position of the ions, you can get basically something that looks terrible to something that looks pretty good. Okay, so that's changing the scan rate of my JB curve. So depending on the position of the ions, I get good charge extraction or pretty terrible charge extraction. So it's basically an indication of what is accumulating at one of the interfaces. Okay, so let me talk some very basic physics that I'm sure you know, but in case somebody's forgotten about this, let me talk about the built-in potential for a second, because this is something that we're going to get out of this measurement. So the built-in potential is when you put a semiconductor between two metals, or something very doped. It's the difference in energy between these two work functions, right? And effectively, that creates a built-in field, right? That normally in traditional p-n junction solar cell you would use to separate the charge carriers. Now, this is important. In a solar cell, the built-in potential of the open circuit voltage of the device is not the same thing. Now, we had to argue with the reviewers about this because apparently it's a big misconception in the field, but you can use the same contact materials with two different semiconductors, and although your built-in potential is 1.1 volt, you can get a voltage of 1.45 out of the cell. What that means is this diagonal difference is not necessarily limiting the open circuit voltage. This is important. It's going to come up in a second. So, okay. So what we characterize with this measurement is the potential drop across the perovskite. We apply. So let me get to the next one. So what we're looking for, as we apply a voltage to the extraction contacts, we basically accumulate one type of ion, and then when we switch, so when we overcome the built-in potential, we deplete that ion from that contact, right? So at first we accumulate, and then we remove it. So then we flip the sign, okay? Because it's always trying to overcome this external bias. So the point where the potential across the electric field across the device is zero is when it's perfectly screening that built-in potential, right? So if we can find the moment where the ion accumulation flip changes, we actually find out the built-in potential of the solar cell. Now, this is an interesting result because measuring the built-in potential of a cell is difficult. You normally have to do something like UPS on layer by layer, or you'd have to build up some very complicated Kelvin probe setup where you find the potential of the surface and so on and so forth. We can do this in a device, which is quite neat because then we don't have to make assumptions. This is what it is. Okay, so how do we measure it? We stabilize the cell at a particular voltage, and then we quickly pulse to a probe voltage, measure the current at the probe voltage, and then we can do this for a series of probe voltages. We can reconstruct the J curve for a given stabilization bias. This is what it looks like. So this curve here is what it looks like. So this one, the yellow one, is when you stabilize the cell at 0 volts and you probe. And then the really dark one is when you're getting closer to the open circuit voltage of the device. So this is the experimental data, and this is the simulation of the same data set. The main thing here is that this goes from being quite, S-shapy to being quite sharp. And there's a transition point between the two. The transition point gives you that built-in potential. So we can use that to characterize a cell. So we basically did some simulation work where we changed the offset of the contact on one of the interfaces and see if we could characterize that with the technique. So this is the prediction from the modeling. This is the actual result. We can show that we can measure, depending on what you stick on the surface, you can tweak the potential, and it does. You do end up getting the different built-in potentials, which is really neat, because that basically corresponds to, like as I was saying, the way you would normally characterize this is using UPS, which is actually not that precise. I don't know if you've ever fit a UPS data set, but we do this whenever we get a paper to review. We go like, let's just pick any points on this line and see if we can get a different onset. Because it turns out that for perovskites, the density of states near the band edge is too low to get a good measurement out with UPS. So it doesn't help. So you get a big uncertainty with UPS measurements. Whereas when we do it with this pulse technique, your error tends to be about 0.1 volts, which is pretty decent. Okay, so when we started doing this kind of work, we actually made an interesting, interesting thought experiment. We actually know at what point the internal electric field is zero, right? Because we can find out using the pulse technique. This is the equivalent of not having ions in the system because they're not playing a role in the electrostatics of the device. So this gives us a platform to look at what would the device be like if there were no ions in it. So we can compare the effect of ions on the actual performance of the device, which is an interesting idea because we can't get rid of them. So we can answer the question: are they good or are they bad? Do we need to, what do we need to do to take the biggest advantage of this system? Anyway, so this is how it would look like when you choose the flat ion, the potential at which the electric field inside the device is zero. Thus, the two devices are equivalent. So we decided to look at that. So we did the measurement, and then we basically did a really slow JV curve. Each of these points in the quasi-steady-state curve is about 10 minutes. So you just hold that voltage until you get bored, and then you move to the next one. Effectively, this allows the ion population to equilibrate, which gives you the JV curve with ions, right? Because that would give you the effect of the ions as each of these voltages. And then we compare that with the pulse JV, where the ions are held constant, uniformly distributed inside the device. So that's the comparison that we're making. Now, a really interesting thing, the device with ions has a bigger voltage. They actually improve the open circuit voltage of the device. And the performance is low as well. You lose a little bit of current. So ions are not great. They make you more sensitive to surface recombination, so you lose a bit of charge at the interface, but they help you screen off these offsets at the conduction band and valence band with your charge extension layers, making them your cells a little bit more efficient. So they actually help you smoothen out these potential differences at the interfaces, which is a very interesting result. It basically means that ions they actually enable us to make better devices. So we shouldn't be trying to get rid of them. We should try to make use of them. Okay, so this was a particular device on a cell that wasn't great. So we thought, okay, let's measure a cell that makes a bit more sense. So something that gives higher performance. And this is this one down here. So when you minimize surface recombination by putting a passivation layer on the surface, you minimize the surface recombination, but you still get a boost in voltage. So ions, even in better cells, they still give you a better response. But we didn't stop there. We went to a group in Hong Kong that makes some of the most efficient devices, and they're making 24-25%, and we took one of the devices and measured it. And basically observed the same thing. Even in their really high efficient devices, when you're getting close to that flat ion potential, the curve with ions is a little bit better. You still gain a teeny tiny amount of voltage, which kind of gives you a bit of an edge. So what does this mean with regards to how should you optimize your device? Well, this is what we kind of took data set using the parameters for this really high efficiency device, and simply looked at picking the surface recombination and the band offset. The interesting thing is that when you've got ions, you're less sensitive to offsets at your contacts. Okay, but you're more sensitive to surface recombination. So if you look at a device without ions, we can make basically a 26% cell all the way up here, whereas this kicks in soon. So it's a trade-off. Solar cells with ions, you don't have to optimize the energy offset so much of your contacts, but you need to be very careful with your surface recombination. This is a bit different to what you would do if you're doing organic solar cells. In organic solar cells, what you really want to get is perfect band alignment at your contacts. If you're thinking of other classical technologies, You want to have perfect energy level alignment. We've been trying to align these levels for 20 years. But it turns out we don't have to. What we need to be careful of is that we minimize the surface recombination. This is the outcome of this study. We can actually show that we need to focus, we're focusing on the wrong thing. We need to focus on minimizing surface recombination. Okay, so I'll move on now to a slightly different topic. So we were talking about how to, ions and what their implications are for devices. The other thing that is really important in perovskite solar cells is the stability. So we've been looking at this for a while now. So basically, you make a device, you leave it in the drawer for a couple of weeks, and you find this. They don't last very long. Let's put it that way. The reason they don't last very long is that water, especially if you don't encapsulate, really attacks the structure. So some of our early work looking at this, we saw that water can actually be part of the crystal. You can hydrate these crystals and then disconnect the octahedra from the corners. And as I was saying earlier, if you change the bond halide angles or the geometry of that bond, you lose your optoelectronic performance. Okay, so basically, when we hydrate the crystals, we just lose conductivity and the rest. The nice thing that we did find out is that water goes in and water comes out, and you still remain with the same crystal structure. You actually recrystallize it by putting the water in. Anyway, so this was just showing that indeed happens. And we did a bit more work looking at the actual specific mechanism. And what we find is that depending on the relative humidity, you've got like it's a bit of a staircase. So below 30% humidity, water just absorbs on the surface. About 40% humidity, it starts going into the crystal. This has implications, of course, because when you're making these devices, you need to keep your humidity in the room below 40%, or you're hydrating your crystals. So that's one of the outcomes from this work. Something else that we're quite interested in is, well, exploring this tunability. I was saying earlier that the only thing that matters is the lead halide bond, right? And then you've got multiple groups basically chucking anything into the casting solution, any atom. You just go like, put some lithium in there, put some sodium in there, see what happens. Anyway, so a classic combination for a state-of-the-art device these days has something like 7 or 8 things. We just chuck it in there. From ammonium, methylammonium, cesium, rubidium. We put different halides, you can put different metals, you can put tin, you can put lead. It's all a big mess. But it makes the device better. Why? So we looked at that a little bit. So we saw that when we added a bit of cesium and a bit of rubidium, our devices did get better. So we went to see, okay, let's start with a simple mixture, just adding those two and see if we can identify what is going on. So the first thing we normally do is, have we made the thing that we think we've made, right? So if you put rubidium is smaller than cesium and is smaller than 4 million methylammonium. So you'd expect the lattice to contract if it goes into the lattice. Same with cesium. Cesium is smaller than methylammonium and 4 million, so it should make the lattice smaller. And indeed, when you look at cesium, you see that your perovskite peak shifts to the right, and that just means the lattice is smaller. Okay, so that's all consistent, is great. Cesium goes into the structure. You put rubidium, it goes the other way. It gets big. That makes no sense. How come the lattice get bigger when I put a smaller thing inside? Well, the obvious answer is we're not putting something inside. What we're doing when we add rubidium is we're taking stuff out. We normally work with a mixture of bromide and iodide. Turns out that it's more thermodynamically favorable to form a rubidium-lead bromide side phase. So we leach out some of those ions from the perovskite structure. So now it's more iodide rich, so the structure is bigger. So the point I'm making here is that you can chuck a lot of things in, you can passively surfaces, and it does make the thing better. It makes the device more efficient. So why? Well, the first thing that we looked at is when we add cesium, your charges become longer lived in your device. Okay, and the mobility goes up. When you add rubidium by itself, they're not particularly longer lived, although the mobility does get a bit higher. When you use both of them, they get longer lived and they're faster. which is an interesting result. So we tried to figure out why. So, okay, so we also did this one's not that interesting. This one's the more interesting one. So one of the measures you can do is you can take your film, your device, cool it down to liquid helium, shine a light on, trap everything that can be trapped, and then slowly turn the light off, slowly heat it up and see how many charges come out at what temperature. That gives you an idea of how deep those traps were to begin with. So anything that comes out really early in the process is a very shallow trap. Anything that comes out later is a deep trap. So the starting material has a lot of deep traps. When you add rubidium, you're not really changing that. This is not significantly different. When you add cesium, see that we've completely removed the majority of the deep traps. So it turns out that when you include cesium in the structure, you heal some of these deep traps, which explains why your charges become longer lived. There are fewer traps recombined, so you end up with a better device. The fact that rubidium and cesium work better in tandem is because rubidium stays on the surface of the crystal, passivating, removing some of that grain boundary disorder. So, okay, so we have this mechanism. We know that humidity is not great for our devices, but we know that putting these things in helps. But we would like our devices to be more stable. So we looked at ways of stabilizing the structure. So our approach is the lasagna approach. So we like to use layered materials. Layered materials are great. Basically, we can form these quantum well-like structures. They self-assemble. You put in the right ingredients, you let it dry, and you end up with this beautiful lamella of these types of structures. So we looked at this particular data set. Is just looking at, well, that's a phenolphthaleammonium molecule. This one is a bulky cation that sticks between the lead octahedra. Okay, and we can control the number of octahedra if we control the ratio of the big cation to the structure that we're using. The more of the big cation that we put in, the thinner the octahedra becomes. Okay, so we can control that. And the properties change. So the more you confine it, the more it looks like a single layer, the more your exciton binding increases. So it's harder to break off those excitons, and then your device physics becomes dominated by exciton dynamics, not free charge, which is what we have with the perovskite. Now, when you make devices out of these, they don't work very well. Charge transfer is not fantastic with these, because normally you'd have charge transfer going in that direction, and you've got that insulating layer in the middle. It doesn't make your device better when you do that. But if you use the lasagna approach, so you put a layer perovskite on top of your film by converting the top surface, you kind of get a bit of both. You get the good charge transfer of the archetypal, classic 3D perovskite, and now my top layer is it's got these really nice big bulky cations, hydrophobic, more stable. We're on the money. Things are looking good. So when we do that, our device becomes a bit more stable, and particularly, and this was interesting, we saw an increase in the open circuit voltage. That's 100 cells of the same type. Because normally with these devices, it's hard the device-to-device variability is high. So you normally go like, okay, you short it once, make sure that actually holds for a large number of devices. Anyway, so when we do this layer perovskite on top, we also passivate the surface. So it makes the device more stable and better. So which was great to see. And it also slows down the degradation. We now have no formation of the layer perovskite when we do this. So this is how it looks like when we've got the bilayer structure. So it does help a little bit. Let me skip this bit. So one of the things that we were looking at is, okay, so this layer structure, it helps you passivate the surface and it makes your device more stable. But how does it work? And most importantly, is it stable itself? Right? We don't want to put another unstable thing on top of our unstable thing. So we looked at these. So we looked at flakes. We made single crystals of these, delaminate, you know how they make graphene, get some sticky tape, delaminate it, and then you can study that material by itself. So you can, this point is a series of the same flake just exposed to moisture over time. What you can see is that a flake that starts quite nice gets roughened up, and you can see pimples appearing and expanding. Okay, so we did the same study on AFM, and you can see that each of these points, each of these pinholes forms and then grows. Eventually, you lose the whole terrace, okay, for these layer materials. So our proposed mechanism is that under exposure to humidity, the structure does buckle, and wherever you've got a defect, you lose one of the cations, that grows now laterally, losing all the cations in that row, ending up with lead iodide. The thing is, that lead iodide you end up with is now insoluble, and it's kind of like tiles. It's like the roof tiles. They're just layering on top of the perovskite underneath. So you don't have the same material you started with, but you end up putting something on top that is more stable. So it does work. It's just not what you think it was when we started doing this, which was a surprise to us. I'm not gonna lie. But anyway, there you have it. That did work quite nicely. Okay, so I didn't want to give you way too much information, but some of the other stuff that you can do with these materials is you can look at terahertz generation. This is something we've looked at with our collaboration in work. You can, of course, look at new structures, LEDs, and you can also make transistors out of these. So they're, I haven't put the citation here, but these are all types of devices you can make, and I'd be very happy to chat about that after the talk. I wanted to focus on just a few short stories and not overload everyone at 3 p.m. In the afternoon. We also looked a little bit at organic semiconductors and how they dope. So that's also, if it's of interest to anyone in the audience, we're very happy to chat about that. But before I go, I want to show you something completely different. So I've been talking about photovoltaics for ages. Let's now take a step back. This is a very tunable structure, but you're not limited to just sticking in lead. You can put something else in there. So if you put an ammonium cation is in there, you keep the same iodide, but you can put something else like this bulky organic ammonium cations. You actually get a perovskite structure, and now you don't have a metal in it. Now, I was talking about that the optoelectronic properties arise from the lead halide hybridization. These do not conduct at all. They're terrible. But they've got a very strong nonlinear refractive index. Okay, so this is a Z scan. So basically, you illuminate your sample and you move it in and out of focus. So you can start up nonlinear processes in your device. So you can look at the nonlinear absorption, and that gives you the nonlinear refractive index. So this is the third order nonlinear refractive index. It's just due to the distortion of the lattice. And it's got a very strong nonlinear refractive index. I'm not going to get into the equation how you fit it, but the main thing is that these materials have a very large laser damage threshold and a strong third order nonlinear refractive index, which actually makes them really interesting for optics applications. The figure of merit, which is normally what you would compare them with, it's actually quite good for these types of materials, and it's about 10 times better than you would get for silicon, for instance. So if you're looking at a semiconductor platform for optics, these are not bad options. Bandgap is wide, so that means they're actually quite stable. And we can grow them in fibers. So this is something I was talking about earlier. We actually can grow these single crystals into the fiber. And you can look at, for instance, second harmonic generation, but there's other things you can do with them. And with that, I think I'll conclude. So just to acknowledge that I also collaborate with these people, and this is my current group right now. So thank you very much for your attention, and hopefully that was interesting, and you've got many questions.
So thank you very much, Pablo. I remind the people that is online that they can also put their questions in the chat or in the question and answer section. So is there any question in the audience?
Actually, I have a question regarding the printing possibility. So you mentioned it's possible to print a perovskite solar cells quite easily. What do you think about printing actually lead-free perovskite? So I'm thinking about the tin or double perovskite like silver would be.
So the tin ones are a bit of a pain to work with. If you're familiar with the literature, they are very oxygen sensitive. They become p-doped very easily. You introduce lots of defects. The performance goes down really quickly. Having said that, you can encapsulate. And you're never going to put a device on a facade or anywhere that is not encapsulated. This is true for silicon photovoltaics as well. I have to say though, I'm not a big believer of the tin-based perovskites. I do think your diffusion lengths are smaller. You're much more defect sensitive, which means when you're actually making the thing, it's always much harder to control. You can get slightly better results if you put a little bit of lead in, so you've got a lead tin mix, but then of course you don't have a lead-free material. The double perovskites, we looked at that ourselves a lot, but because of the way your electron mass is huge, so it just moves very slowly. So your charge transfer just goes down the drain. You can get them to work 6-7%, but they're just never going to be stellar. Now, I should say that this is a huge concern, I think, a huge concern back in the day. I don't think we're so concerned with toxicity as much. And the reason I'm saying that is because you're putting in 200 nanometer thick film. You're going to have more lead in your device from the joints that you actually solder together than the actual amount of lead you've got in the film. It's a teeny amount of lead. I had some minions pushing some solar cells into the lake, and did the maths for like, if you pushed something like a whole solar park worth of solar cells into, what was it, one of the lakes near Munich, I forget what it was, how much lead would be in the water, and would it be toxic enough for humans? Turns out it doesn't change it very much, because there's not a lot of it. We've put way more lead into the environment by driving the leaded fields back in the day. So there's way more, right? You can't, like, the point I'm making is concentration of lead in the soil is already bigger right now without putting the solar cells than if you, like, it doesn't change it very much. So I think as a field, we're less concerned with it than we used to, yeah. Because if it works, it does generate electricity cleanly, and it can be recycled. This is something we've shown some of my work as well.
But what about printing? Do you see any differences
in
printing those two different classes of the perovskite?
In terms of the film formation, you mean? I mean, they crystallize differently. The double halides, the double silver bismuth, they are much harder to crystallize. You gotta go to higher temperatures. So they're a bit trickier to work with. You can still print them though. It's all about controlling the process. The tin ones also crash out very quickly. So it's, again, you need to work with a solvent environment. I think it's a technical challenge rather than a technological challenge, if that makes sense. It's solvable. It's not. I don't think it's that's not the thing that's stopping us from getting them out there. Let me put it that way. Does that make sense?
Yes.
If I may add something that, because I worked many years in perovskites, and the reality is there is actually just one, maybe two works out with large area. It was actually a guy from Castellón in the Universidad de
Biscayne.
No, Ivan.
Ivan.
One of they collaborated with Saulet in Poland, and there is ACES energy letters out in that they did large area, and they struggled, but I know the person here, the first author, and second, they struggled a lot because there is only one that, and I don't remember the technique, but it was large area, and also apart from that, if you plot the like, of course, the cell area, the smaller it is, the easier it is that it will be more efficient. So people abuse the bit of that, and for that happens for left, but for thin it's even more.
Yes, I believe that.
And for example, I worked with 0.1 centimeter square,
Yeah.
and it was a pain. I could almost never get out of 10. But then you see the records, it's like 0.04 or something like that. And also, yeah, even though you can have all your like conditions control, the crystallization, even in small scale, it's just it's much more restricted in terms of the conditions that you can use. And on top of that, then it exposes the nature itself of the materials that hasn't been so much explored, makes them just crystallize faster, worse, and thinner. It's just much more challenging. And I also I agree with the fact of the toxicity, because I think they're interesting enough not to blame lead, so that we studied it.
I mean, I had a couple of students looking into the crystallization of the tin perovskites, so I kind of burned a student. So I'm not doing it again. And it was just that it's very hard to, like, even if you get the perfect film, the defect chemistry is against you, which is why I think I don't want to say it's never going to work, because somebody might get it to work, but I think it's so difficult that would ever become the large area technology. The scientific, the technological challenge from the defect chemistry is so much more difficult. Like, you have to put in oxygen scavengers. I mean, if you work with it, you've definitely added random stuff to your casting solution because it scavenges oxygen. And that it also doesn't help with the crystallization, because then you got seeds and then it's even harder to control.
But actually, what I've seen is that it is so complicated, so defect sensitive, that, and you can see in the literature, you can put anything, you probably improve it, but in the end, then it's not stable.
That's the point. I like I said, I burned 2 students on that. I'm not doing that again. I don't believe in it. I really don't believe in the tin perovskites. Lead tin, it can work, but the pure ones they're just too defect sensitive. You're never gonna use that, being perfectly honest. I mean, that's my opinion.
Any other question, comment?
Thank you for the good presentation. It was very interesting. So I'm just interested in the stability of perovskite crystals, and I think there is lots of studies about the stability under humidity. But have you also studied about the stability under illumination?
Yes.
And yeah,
So
do you know what is the main factors affecting the
okay, so it's convoluted. It's convoluted. So under illumination, ion migration speeds up. So and if you've got a mixed system of iodide bromide, for instance, they move at different rates. So you end up with halide segregation. That's well documented. You can stop that by putting different things in the cation. So if you alloy it from the cation side, you can increase the activation energy for Halide migration, and that helps to stabilize the system. This is also the only way you're going to get to those high band gap materials. What causes how does it degrade? Again, it's a complicated process. Normally it starts at the grain boundaries, right? And in the charge extraction layers, those ionic vacancies can catalyze the formation of some superoxide species, and then you start losing your cation, and then that just comes off, and then you're left with just lead iodide, right? So that's game over at that point. I mean, it's not super clear how it works, I think. We all have different ideas of how, at the end of the day, when you put light in, everything is moving quicker, so you kind of speed everything up. Water goes in and out, but water kind of catalyzes that degradation. So when you have an electric field on and light, you can change the band gap by like almost about 100 electron volts because of that halide segregation. It's quite neat, actually.
Yeah, there was another question.
Yeah.
You wrote ions improve physics.
Yeah.
But Well, I mean, first of all, and probably you mentioned, but I don't remember exactly maybe how, but for like regarding also interfaces, and so it is very dependable on the charge transporting layers.
Yeah.
But then also, is it possible to have all these ion movement phenomena and have a stable device?
Okay, so that comes to the key of the question. Are your charge extraction layers, whatever's at the interface, that stable? So I think the current generation of materials, they are putting things in the passivating that surface. And I think that makes it electrochemically more stable. So you can see now there's, science papers coming out all the time with like 26% stable over like 10,000, 20,000 hours. I do think it is stable. When you mentioned that it's depending on the charge extraction layer, this is true. But it's not just because of the band offsets. It's also due to how that changes the surface recombination. So not every material that you put on is going to be good at extraction charge. And for instance, we worked with, these azomethane materials that just had super high surface recombination. We still couldn't figure out why, but they have a thiophene kind of moiety on it, and we think that the sulfur group sticks on the lead atoms, and that generates interfacial traps, and that was just a kind of a recombination layer. So yes, it depends massively on what you choose as a charge extraction layer. What we were wanting to say is that the offset is not the key thing that kills it, is that surface recombination. So as long as you can passivate the surface, or you choose whatever Hall transporter or electron transporter that doesn't do that it mitigates the surface recombination, your device with ions is more tolerant to a wider range of offsets. I think this is a cool thing. I genuinely think this is a cool thing. I think this is why we've been able to make good devices, though not great, from the start, because it's just so tolerant. We started with this in 2012. You could literally put in anything and get a JV curve out. I'm talking way back before the science paper. I was working with Henry Street in Oxford, and I put vanadium oxide. It was just some random thing I had lying around the thing, and it worked. It wasn't great, but it worked. I put PDOT, it worked. I put PCBM, it worked. I put literally anything. It works even without charge extraction layers. You can put gold and FTO, and it works. It's not great, but it works, because those ions will help smooth out those offsets. So the energetics work. The hard part is that minimizing that surface recombination. That is the hard bit. And that's where your Hall transporter, electron transporter is really important. It needs to be able to get the charge out. It needs to be conductive enough. It can't introduce any traps at the interface, or it won't work. If, for instance, when if you work with it, you work with spiral that. You need to add salts to that to dope it. Those salts migrate to the interface, and there you have it. You got lithium ions near there, they'll mess up your interface. You can see that now the field is moving towards PIN structures using more stable underlayers and using evaporated C60 and PCBM materials on top, without the addition of those salts to dope the charge extraction layers. Because that, again, is minimizing that surface interface, surface recombination. It's the whole field is doing it, but we don't know why. It turns out that's the thing that works. But why? It's because of that. Your ions basically screen off those offsets at the interfaces. So the energetics matter less, which is something that is very unusual. Any other photovoltaic technology, if the offset is not right at the interface, it doesn't work, because you get the minority carrier accumulation, and bam, that's a recombination layer. So getting the energy. So I used to work with Dyson-sensitized solar cells. You have to get the energy levels just right. We were tweaking, but like you would chuck almost anything in there to really fine tune the energetics, just so you get the optimal extraction and injection. It was all about energy levels. Turns out that's not that important. Not just from my work. I mean, obviously I believe in my work, but the field is going in this direction. Everybody has decided that the thing that makes the biggest difference is passivating the surface. And the reason is that ions help you to make it work. It's a bit crazy to me, but it's how it works.
Okay, any other last quick question?
I have
Yes.
a question, but maybe it's not so quick.
Oh, okay.
Okay, so maybe it's a follow-up
Yeah.
to this. Why not to use as a charge transfer both electron and the whole transport layer, like something based on the graphene? You can easily dope graphene and it's
Yes.
stable. You can keep safe your perovskite
yeah.
inside.
So we did this back in 2013, 14 was it? Yeah, I sent a student to Cambridge, working with, what's his name? Ferrari? Yeah.
The one with graphene.
Yeah, the graphene guy. We just go like, yeah, put some graphene electrodes on it. Didn't really work. We tried so hard. I don't really know why. We couldn't figure out why it didn't work, but there's something about that interaction. The perovskite, you've got those of ions sloshing around, and graphene is also very easily, like any atom you stick on the graphene changes its properties massively. And it's just, I mean, it's a single layer, right? So I assume that as you get the stoichiometry perfect, like you think you've got something, but when you put it on top, you've got a different thing. Because ions will move to that interface and modify it. So I think that's why it doesn't work. But sure, I mean, in principle, it was a great idea. Try for 2 years, couldn't get anything to work. I mean, you can get something, you can always get something to work, but it wasn't really convincing. It wasn't great. I mean, we got at 20% something, but it was just not great.
Okay, so thank you very much again, Pablo, for being here and for this very interesting talk. Hope to see you soon again.
Excellent. Glad you guys enjoyed it. Happy to chat with anybody if, I'm here, so.
I have another question.
Yeah, sure.
I didn't introduce myself. I was actually also a part of the Johann Feldman group.
Okay, you're in Feldman, right?
I'm also your co-author. In 2016, I think it was a paper on Gavante. So
Oh, the Lakshmi's paper, was it?
yes, exactly. So I did this all the modeling basically for this paper.
Well, there you go.
Later on, I went to Cambridge, so I know how to draw some strands.
Yeah, well,
exactly.
yeah, exactly. I mean, we said we were. Do you remember Luis Miguel?
Yeah.
We were trying so hard to get the graphene thing to work. It just didn't work.
Okay.
It was a pain and so difficult to work.
Okay.
Such an absolute.
No, but later on, I think in 2016 or 17, engineering department in Cambridge, they managed to publish a work when they put the graphene actually as a, I think, electron transport layer, and it worked.
I mean, this is the thing about graphene papers. This is the thing about graphene papers. Just take graphene on something.
Perovskite solar cell with graphene.
I don't agree. What I'm saying is, you can put graphene on stuff. You try hard enough, you get something. You always get something, and you can get a high impact paper. There's loads, but you look at the people making the 26% cells, and they're not using graphene. They're also not using spiral.
Yeah.
So, like, okay, the field might not say, that doesn't work, whatever, but like the people that are making the good cells, they're not using that. And
it can be misleading to just go in the without being very aware of the literature. Oh, so this seems to work for perovskite.
everything works.
Yeah, exactly. So,
Everything works.
so
It's super confusing. Everything works, and then you try it, it doesn't really. We had this recipe.
Because perhaps the YouTube is still. I don't know.
It's fine. I mean, I'm not saying anything that not. We had this recipe that used hydrogen acid in the casting solution, and it worked great because it solubilized all the components and it slowed down crystallization, and it gave you this beautiful shiny. You could see your face in that. It was beautiful. Never worked. Couldn't get it. But not even 0.1%, which is like rare. Nobody gets something. And they were publishing these 17-18% cells at the time. I'm talking 2013. That student finished a PhD. Nobody ever did it again. You're like, well, sure, everything works, but if the same lab that develops it doesn't even keep with it, it's not great.
yeah, in the end, at the beginning, it was a mess.
Oh man.
But the time really, it was kind of a filter, and now you see back in time, and now you see what really worked and what it really didn't.
I think we know a lot more about device physics now than we did back then. Back then, it was all a bit random. Because the thing is, it always works somewhat. And then you end up optimizing things. So the way this works normally is you get a student that they try really hard. They make lots of devices like that student in Castellón. They'll get one device that works. They'll get a paper out, and they'll never touch it again because, well, that was horrible. But then somebody else just picks that up and looks at it, and it's just always a bit of a mess. But the thing is, because you end up working so hard to optimize the system, you end up hitting the conditions where you unknowingly are choosing the thing that makes it work, even though you don't think that you're doing it. For instance, for the layer processing top, I think we were I'm not saying the first, definitely among the very first to use that interface. Like that's a charge abstraction there. And now it turns out that people are thinning it down to the point there's no layer structure anymore. But they're still calling it a layer processing, they're still looking at the you can still see it in the X-rays, just there, a little peak like that. Turns out when you use chlorobenzene with a little bit of something on top, you actually wash it away. What you've been doing is modifying the halide composition on the surface, which shifts the band offset to a point where it actually makes it better. But you don't know you're doing that. You just see that your device is getting better when you reduce the concentration a little bit. I think this kind of stuff is we stopped focusing on efficiency a while back because you could get anything. And it was depressing.
And it's also not nice to just go and do blindly
chuck some items in and it will work. So we've always focused like, okay, chuck stuff in. What does it mean? So we've been able to get some of the devices, and I really think it's not that we cracked it, but we know a lot more. And I think that helps in this kind of work. I think it's important because otherwise we're always just random. Like, you don't know this. They were like the explosion of the process in 2012, 13.
Yeah, 13.
And every PI everywhere in the world that was working on anything remotely related to organic semiconductors, solar cells, etc., had a PhD student mixing lead salts with random iodide salts, throwing the dice, and then you got do dice. It was an absolute mess. Anyway, it's an interesting field though. I think it's got a lot of promise.
Okay, so I'm just like out of the curiosity because I'm also like in the carbon field a lot. So if not graphene, what do you think about the carbon nanotubes?
So we tried that. You can do funky stuff. You can do all kinds of funky stuff. I mean, we tried all this stuff back in the day. You can have carbon nanotubes embedded in a very hydrophobic matrix, right? To the point where you can put it underneath a water stream and it won't go in. I think it can, for sure. As long as you keep the device tolerance correctly, like you have to choose the right offset. You can't be too far out. I mean, if you want to get a 26% cell, you got to be within 0.2, 0.3. I mean, that did come out of the model. Sure, it's tolerant, but it's not, you still has to be reasonable. Carbon nanotubes are not great, they're not fantastically selective. So you end up with surface recombination. And that's the thing that does come.
In the end, there is a problem with the organic semiconductors that you want to apply as an interface and as an interlayer or transporting layer, whatever. That you have to think of a lot about the geometry that it has. Of course, its character as a semiconductor, but also its geometry. For example, fullerenes are the main one being used in that kind of structure where you use these electron extracting selective layers. And well, I mean, I don't know if it's true for all the carbon nanotubes and for all the carbon molecules, but the geometry makes them. I mean, from the fact that it's maybe one or maybe 2, 3, it's these adult molecules, and so
PCBM, that thing sticks to itself. PCBM exposure to UV, it'll dimerize.
Yeah, in fact, and a lot of people are concerned also about the stability of.
I mean, the organic semiconductors are interesting. I think it's a very interesting field, but they're a mess.
But for example, in the for fullerenes, people even like tried these adults or and like different isomers, purifying the isomers, and already there you can see a difference in the energetic disorder that you will have. So I assume that other carbon allotropes, maybe some carbon nanotubes for graphene, that is a mix of
Yeah.
hundreds of molecules.
Some chunks, that was, if you met Sam, that was his PhD. Separating out the carbon nanotube, that was what he was trying to do for ages. It's not simple. I don't know. It's not that I don't believe in it. I think if you want to have something that you can just coat at large scale, carbon nanotubes is never going to be it. There's too much disorder. Like, how do you get selective in a ton scale?
Well, there are some methods actually. I'm also publishing even recently works how you can actually with 100% efficiency select like particular, plurality of a semiconducting small nanotubes. That's the issue, right? But that is not an issue.
Yeah.
So you can do that. I don't know about the high scale, as you are saying, tons. Yes, of course, but yes, but there are methods, even cheap methods. You can actually pick whatever you want.
Right.
Yeah.
I mean, I couldn't stop looking into that direction because it was always messy, could never understand it, and it was so variable.
Yeah.
And the process itself is variable enough that it was a bit like I could never get anything solid out of that. Not saying there's easier things to work. Evaporating C6, it turns out to be one of the easiest ways to put it down. So it's just what most people end up doing.
No, because hypothetically, I was like thinking because you have like so many different materials in this perovskite solar cell, like the contacts, the electron transport layer, etc., like encapsulation layer.
Yeah.
So you have even the substrate, right? Everything is different. So you have interfaces, right? But if you like accept the perovskite, you can use like just carbon allotropes everywhere. Like then you get rid of, all this.
There's a group in Swansea using carbon black as an electrode. I mean,
Carbon black.
it's a med. It's a med. They take carbon plate and apply it.
There.
It's everything. It's an absolute med. But that somehow kind of works.
Okay.
So what you do is do electron excitation layer like titanium. You put an insulating like zirconia, and then you put your carbon black, and then you go around and add the perovskite to that, and then it dries inside the network, and that works.
Okay.
It's not great. It's not great.
Yeah.
But it works. Like you can get 17, 18, 19%. And that's almost as cheap as that's ever going to get because it is literally just, it's a process where you just print different layers. I don't know. You can go the high efficiency route and then we're tweaking, the surface recombination like crazy, and then sure, then you can design something that will be just right. I think that's not where this is going to go.
Okay.
Because you can't crystallize the perovskite with that kind of precision at the large scale.
Okay.
And if you're going to get a high efficiency device, everything needs to be just right. So I don't think that's where we're going. I think what we're going to do, not just because I did the work, obviously I believe it, but making use of the ions instead of trying to get rid of it. Well, use it. It's there. Why go to the composition that minimizes the effect of ions and forces you to make all these extremely difficult optimization protocols? Use something simpler, get something at the interface which is what you want it to be roughly, and then you work with something that's easy to crystallize. That's going to be much easier to optimize. I think what we're going to be seeing in the modules, actually, if you look at the modules, what do they use? They don't use seeds from homogeneous, repeating method ammonia. It's not that. It's FAPI or MAPI. Why? Because it's the easy one to crystallize. It's what works at the larger scale. Because getting those films just right, you send us to this is crazy. I sent my thing to Hong Kong to do the device work because we're like, I don't want to spend 2 years doing the optimization when I can just send someone to the devices. The student is really happy because 24%, everything's working great. Comes back 12.3%, same recipe, same chemicals. Doesn't make any sense. It's because it's so finicky, the crystallization of these difficult compositions. It's so like intricate. Just something a little bit out of range, and it crystallizes different. Now you got different things at the interfaces. Now your defect catalyse is different. Now you optimize your layer for something slightly different. Now of course your separate combination is different. But it doesn't work. Well, it doesn't work. It works, but it's not 25. But it's not 26%.
I did a postdoc in Antonio Abad's group in
Oh, yeah.
Berlin.
You met Antonio?
Maybe you met him in.
Of course, we were working on DICEs together. We put a paper together. My PhD was in DICEs. It wasn't on perovskite.
In fact, I have seen your name for a long time. So I was working with him, and we were. It is a mess.
I burned so many.
I don't know anybody. That of course it's not from Asia because they are much more constant. But I don't know any European that has worked on it and kept working in academia.
No.
They all.
No, you get burnt out. You get burnt out.
Yeah.
You get absolutely burnt out.
And then we were making some like even 7% without DMSO.
That's not bad.
Without DMSO.
That's
So
not bad.
like we were trying because oxidant, blah, blah, blah. And it worked super nicely without any additive at all. And it worked on I did 3 batches, and then they moved the glow box to another room.
You know what it is? The temperature. It's the temperature of the box. I'm telling you, that's the temperature of the box.
I also played with that. It was impossible to. Then it was 0. Then it was like the films didn't look well.
No. It's true.
I did it in the dark because there was a window. So I was like, maybe it's the beauty.
I wouldn't be surprised. The tin ones, I don't know. I saw so many people trying so hard because lead is so terrible for you, which is true. But everyone was trying so hard, and it just doesn't work. I mean, I burned to students. I talked to all the PIs. No, we tried. Yeah, no, we got a paper and never touched it again. And you're like, okay, this is why the field is messy as well, because it's all very hard to reproduce because it's not reproducible. And I think this is why we're going back to mapping and fabric genuinely, because it's the one thing that translates across labs. Every lab can get mapping up to 18–19%. That's the one thing that's a constant across every lab. Same with the formation method when it makes that one works quite. It's very easy to crystallize. So that one works.
But I mean, also the most simple things are also the things that are tried the most.
Yeah.
So
there's a bit more on that, yeah, true. But honestly, you try the same recipe in the Nature paper from the Sargent group, which they keep producing these 25.6% cells. You go into, this is depressing. You go into the methods, and they have a different perovskite when they're doing the stability test and when they do the high efficiency device. And then you look at the stability that is normalized, and you're like, come on.
Yeah, we can keep talking about other groups as well, but it's on. So
Well, they should know better. They should know better. You shouldn't do that. I'll get my stuff. Maybe we should.
So that was yours?
No, that one is.
Okay.